Chapter 7, Kinetic Energy and Work. So, the last couple chapters we've been talking about forces and how they sort of move things around and all that. But forces do more than just accelerate things, like Newton's second law, F equals ma. They actually, if you want to introduce a very powerful concept in physics called energy, forces actually are responsible for transferring energy from object to object, or into an object, out from an object. So energy is a very powerful physics concept. We're going to learn that especially in Chapter 8 when we talk about conservation of energy. It's going to be the most important concept of the year. But we're not going to forget forces. We're not going to forget kinematics equations. We're not going to forget a lot of that stuff. It's still here. But energy is the next step. Three main concepts, although there's in this chapter, although there's quite a bit of stuff in them, especially in the work concept. But the first form of energy we're going to talk about in this chapter, we'll introduce more next chapter. The first form is kinetic energy, Ke equals 1/2 mv squared. Then we're going to move on to work and talk about how work is a transfer of energy via a force. If the force is constant, work takes this form. And in particular, if the force and the displacement that an object undergoes because of that force, if they're not parallel or perpendicular, then the work is diminished by this amount, the cosine of the angle between them. Work is a scalar. This is a scalar product, dot product, often called. So direction doesn't matter with work. You can add up different work amounts like regular numbers. We're also going to talk about how work is a change in kinetic energy and in equation form. If kinetic energy is 1/2 mv squared, if your kinetic energy is changing, you're going to have a final kinetic energy and an initial. Work in general, if the force is not constant, work is the integral of a force with respect to position. So some forces, for example spring force, will depend on your position, and we'll talk more about that. And of course, calculus speak, integral is the area under a graph, so work is the area under a force versus displacement graph, or position, I guess you could say as well. In talking about springs and how springs are a non-constant force, we're going to use Hooke's law, which is the description of how force depends on spring displacement. Spring compression or stretching is another way of thinking about it. And this is the expression for the work due to a spring. And finally, we're going to talk about the rate of change of work, how quickly work changes, and that's probably a familiar term to you, power. Although what you may think of power is maybe slightly different. The everyday use is not necessarily equally aligned or well aligned with the physics definition. But this is also calculus. This is a derivative. It's being a derivative, you're going to get the slope of a graph. So that's pretty much chapter 7 in a nutshell. Three main concepts, and let's get right into kinetic energy. Okay, there we go. So kinetic energy. Kinetic energy is the energy of motion. Whenever something is moving, we say it has kinetic energy. Now, when a lot of you have sort of struggled with relative velocity and realized that from one frame of reference, something may not seem like it's moving. For example, as you're sitting or standing or in whatever position you are watching this video, you're probably not moving around with respect to the ground. So you might say you have zero kinetic energy, although you may be like moving the mouse around with your hands, so maybe your hands or your fingers have kinetic energy. But in general, you as a whole may not have any kinetic energy relative to the ground. But relative to the sun, you have plenty zooming around the sun as the Earth orbits. So while not particularly important for this chapter, it's good to keep in mind that velocity is relative, and so kinetic energy is relative in a sense. But it is the energy of motion, and it has a very interesting form. It's 1/2 times the mass of whatever object you're talking about times its velocity squared. Pretty simple. And the unit of kinetic energy, which is the joule, abbreviated with a capital J, but this isn't limited to kinetic energy. It's actually all forms of energy have a unit of a joule. And that's pretty much it. We're going to be doing a lot more with kinetic energy in Chapter 8 when we talk about conservation of energy. But for now, we're just going to simply deal with it as the energy of motion. The next concept is work. Work is essentially transferring energy. When you either transfer energy into an object or take energy out of an object via a force. So when a force acts on an object, energy is either put into it or taken out of it, and that transfer is called work. We're going to look at it in a couple of forms. First, we'll look at it when a force acting on an object is constant. When a force acting on an object is constant, then the expression for work is force times the displacement of that object. So for example, here's a little bead of a certain mass, and we're going to apply a force to it in this general direction, and it's going to move the bead from here to here, and the displacement vector is this blue arrow here. And so this force times this displacement is going to give you the work, although this force being at an angle makes things a little more complicated, but we just have to introduce the dot product. When the force and the displacement are not parallel or anti-parallel, if they're any other angle besides that, then you can use this expression: F times the displacement, force times the displacement times the cosine of the angle between them. So as you can see, cosine is a maximum when the angle is 0. So either the force going this way or going this way. And minimum when it's perpendicular. So if the force is up that way, you get no work done, interestingly enough, because that won't put any energy into it, or take any energy out of it from that force in particular. Now that'll be more clear when we talk about gravity, but we'll get to that later. So long story short, work is a scalar. Direction doesn't matter. This is called the scalar product, and so when you multiply these, you end up not with a vector but with just a magnitude. So direction doesn't matter, and you can add up different work amounts like regular numbers to get the net work. And depending on your angle, work is either positive or negative. So, for example, let me just erase these real quick. As you can see here, this force in general is acting in the same direction as the displacement. What that's going to do, as you can see, so here's the initial position, here's the initial velocity of the bead, here's the final position, here's the final velocity, and you can see that the initial kinetic energy has grown. The final kinetic energy is higher than the initial kinetic energy. So this must be positive work. We've put energy into the bead as it's gone from here to here, which should make sense, because when you put a force into an object in the direction of its motion, you're going to be speeding it up, so the kinetic energy would increase. By the way, you can probably also see that the dot product really is just giving you the component of, that's messy, the component of the force in that direction. So this is really giving you Fx. Let me make this a little thinner here. Fx. That might be too thin. I don't know if you guys can see that well. Anyway, so really we just want the part of the force that's in the direction of the displacement. And so you can see, because this force component here is in the direction of the displacement, it's going to speed up. What happens if we put the force in the opposite direction of an object, if it had an initial velocity, it's actually going to slow down. We're pushing against it. This might be like a friction force, for example. And in this case, the kinetic energy would drop, and we would call that negative work. Negative work. Gravity is another example of a constant force, at least near the surface of the Earth, or any celestial body. And so you just replace the force up here with the force of gravity, mg, and you'll get the work due to gravity. And you can see on this apple here, this apple is falling. Actually, no. According to the displacement here, the apple is going up. So this might have been thrown up. In other words, we gave it some kinetic energy by throwing it up, and once it left our hand, it would be only under the influence of gravity, and so it's going to slow down on the way up, right? So you can see first off the kinetic energy is decreasing, which makes sense because the speed is decreasing. Gravity is acting down, which is opposite the direction of the displacement, so that's called negative work. And negative work takes energy out of an object, and so in this case we're taking kinetic energy out, and the apple slows down on the way up. I'm going to stop here. I'm going to try to keep my videos around 10 minutes or so from this point on. Stop here and maybe summarize work before this part of work before going to the next part of work. So let's do that. See you soon.